This is part 4 in our series of lectures on section 4.2 dealing with the construction of functions. In this lecture we talk about restriction and extension of a function. Restriction and extension of a function are two ways of constructing new functions from given functions. In the first definition I tell you what is meant by restriction of a function. So if we start with a function from set A to set B and we give ourselves any subset of A, so that's sitting inside the domain, then the restriction of f to c, and it's denoted in this way, f, you put a vertical line and then you put a subscript of c, is defined to be the function from c into b such that each x maps to f of x. So all you're doing is you're just simply restricting the domain of A down to a conceivably smaller subset of A. And that gives us a new function. It's called the restriction of f to c. So for example, if we take the sine function, so the sine function is a function from the reals to the reals, each x goes to the sine of x. Now here I've indicated, just to show you the new notation, here I'm taking the restriction of the sine function to this closed interval from minus pi over 2 to pi over 2. I'm just simply restricting my domain to this interval from minus pi over 2 to plus pi over 2. Now why might I be interested in doing such a thing? Well, if you look at the graph of the sine function just from minus pi over 2 to plus pi over 2, you'll see that it's an increasing function. It increases from a value of minus 1 to a value of plus 1. So it takes all of the values that the sine function takes, but it takes each such value exactly once. And so it becomes what's known as a one-to-one function. And in some circumstances you might be interested in restricting the domain of a function which isn't one-to-one so that it then becomes one-to-one. So this is one device for doing that. Here's another example of a restriction. Take the function from the open interval from 0 to infinity to the reals given by x goes to 1 over x. Oh, and by the way, I've just noticed that there's a little typo here. This arrow should be an arrow with a little vertical line on the left side, right? It's the x maps to 1 over x notation. So I made a small mistake there. Sorry about that. Then you'll notice that when x gets arbitrarily close to 0, which it can do given this particular domain, the 1 over x gets really very large when x gets close to 0. And suppose for one reason or another you want to look at f, but you want to somehow make it a bounded function. And so you can't do that if you maintain the same domain. And so what you do is you restrict your domain to a subset of this in such a way that the new function, the new restricted function, becomes bounded. And so if you take g to be the restriction of f to the interval from 1/2 to infinity, so you're bounding x away from 0, right? You're not allowing x to get too close to 0 by doing this. Well, then you get a new function. It agrees with f, at least on this part of its domain, but now it's bounded. G is in fact a restriction of f to this particular interval here. Now let's talk about what we mean by an extension of a function. Suppose we start with a function from set A to set B. Then a function g is called an extension of f, provided the domain of g is conceivably a little bit bigger than the domain of f, but when you restrict g down to the domain of f, you get back f. In other words, g is called an extension of f, provided that f is a restriction of g. So f is essentially the restriction of g to this smaller set, domain of f. Let's give an example of such a thing. So if we take the function f from this interval, this closed interval, into the reals given by x goes to x, so I guess it's the identity function on this interval here, then here I'm giving you two functions, each of which is an extension. Define g1 from R into R by x goes to x. Then if you restricted g1 to this interval, then g1 and f would agree, and therefore g1 is one possible extension of f. But if instead we define g2 to be the function from R to R given by x goes to absolute value of x, that's also an extension, because if we restrict g2, if we restrict the domain of g2 to be this, then absolute x and x agree, and so g2 is also an extension of f. So I guess it's pretty obvious, this illustrates a pretty obvious fact, that a given function can have many possible extensions. Here's a more interesting example, and this is an example that we'll make use of in the next chapter when we talk about cardinality of sets. So let's start with three sets, A1, A2, and B. And suppose we have two functions. F1 is a function from A1 into B. F2 is a function from A2 into B. And suppose that these A1 and A2, these two sets A1 and A2, are disjoint. Their intersection is empty. Well then, it turns out that F1 union F2 is in fact a function. I guess I haven't written it as f. So let's call F1 union F2, I'm going to denote it by f. Then in fact, f is a function from the union of these two domains, A1 and A2, into B, and it's given by this. If x happens to be in A1, then x maps to F1 of x, and if x happens to be in A2, then x maps to F2 of x. So that function is in fact F1 union F2, and it's a construction of a new kind of function from the given functions F1 and F2. And we can do that provided the domains of these things have no elements in common. That turns out to be quite a useful construction. So notice that this function F1 union F2 that we've just constructed here is an extension of both F1 and F2. And so this illustrates the idea of extension. Now we can generalize this example in the following way. You see, it's not necessary that we just do this with two functions. We could have a whole bunch of functions with a whole bunch of domains. And for example, if we had three such sets, if we knew that any two of them were disjoint, then we could create a new function from the union of those three sets by mapping x to F1 of x if x is in A1, x to F2 of x if x is in A2, and x to F3 of x if x is in A3. So we can do that for any number of functions, assuming that the domains are pairwise disjoint. But in fact, we can do that for even an indexed family of functions. So that's what I'm going to illustrate with the following example. Suppose we have an indexing set delta, and we have an entire family of sets that are indexed by that delta, and we'll give ourselves B any set. Okay, so I'm trying to generalize this whole formalism up here, but if instead of just giving me two sets, I'm giving myself an entire indexed family of sets. And just as I wanted those two sets to be pairwise disjoint, so here, for any pair of indices in my indexing set, the corresponding sets should also be disjoint. So now I'm going to give myself, for each element of my indexing set, I'm going to give myself a function, I'll call it f sub I, from a sub I into b. And we're going to take a to be the union of all of these a sub i's. And then I'm able to define this function capital F from the union of all of the a sub i's into b in the following way. We map x to f sub I of x, provided I is the unique index in the indexing set such that x is an element of a sub I. It's unique because we've assumed that the sets themselves are pairwise disjoint. That then gives us a function. It's an extension of each of the f sub i's, and it's a generalization of this example here.